Hello and welcome to Coffee with Caleffi. Our topic today is applying balancing valves in hydronic and plumbing applications. For reference, we have a couple of design journals that you might want to take a look at. Hydronic balancing in hydronic heating and cooling applications, number 8, and also domestic water heating, hydronics, number 11. Also, a year and a half ago, we had a webinar with guest speaker Julius Blanco, who taught us about commercial hot water recirculation systems using thermostatic mixing valves, recirculation pumps, and balancing valves. You might want to take a look at that for reference as well. So let's jump into it. Here's a photograph of a typical hydronic balancing situation. We have encircled a number of air handlers, and each air handler has some type of a heat emitter going through it. Through the plenum on this air handler, you can see, as an example, a coil. And it's the flow rate through that coil that we're looking to balance to provide the optimal conditions for the heated space of this, in this case, a commercial gym. Now, when we balance, we need to know the effect of flow rate on heat output in a heat emitter. And it's not a linear relationship, it's a non-linear relationship. So if we take, for a starting point, a convector, call it a baseboard, and we simply took a pump, a variable speed pump, and sent high temperature water through that convector and measured the amount of heat output as we change the flow rate on that convector, we get a relationship that looks something like this. You can see quickly it's very non-linear. As we increase flow rate, heat output increases, but there are parts where it increases very quickly and parts where it increases very slowly. At heart, what's going on here, a couple of things. Heat is increasing as a result of the convector temperature increasing on average as you increase the flow rate through that convector. So that's one thing contributing to this characteristic or behavior. Also, the effect of turbulence. You can see up until 2 GPM that the rate of change changes quite a bit until after 2 GPM, then the slope changes very little. And the combined effect of these two phenomena generate this type of curve. Now, this part where we're not quite fully turbulent, where we're going from laminar turbulent to turbulent, is what we would refer to as the heat output is very sensitive to flow, and the distribution efficiency is low, meaning for every BTU that we're delivering into the building, the cost from an electrical standpoint is relatively high. Conversely, as we get onto the flat part of the curve, our heat output is not so sensitive to flow, and the distribution efficiency is relatively higher. And then you can see here that as we increase from 5 GPM to 6 GPM and on to 8 as an example, we get very small increases in heat output. So it really doesn't appreciably change the effective output of our heat emitter by increasing our pumping, and as a result, we call this part of the curve the wasted electricity side of it, where distribution efficiency falls off quite quickly. So what we want as designers is we want to set flow rates on our circuits to be in the target zone of our heat emitter. Most manufacturers will publish where that is on their equipment for whether it's a coil, an air handler, or a heat emitter of some sort like a convector, and that's really the sweet spot. Now let's take a look at a fan coil by comparison to that baseboard, and here we have cool air coming in. It's being heated by way of a hydronic coil here and heating the space here. And if we just changed, had one variable, and that was simply the flow rate at which fluid travels through this coil, and we measured as a function of that flow rate the heat output, we would get a curve that looks something like this. It looks pretty similar, doesn't it? Very nonlinear. It doesn't have quite a sharp turn on it here, but a very similar type characteristic. And we can see as our flow rate increases here, so does our output. Very sensitive flow rate, changes the flow rate down here, less sensitive down here. A typical nominal flow rate on this particular heater emitter might be 3 GPM at a certain delta T, for example. And let's say that is the case in this case. So we got 3 GPM, kind of our target, and that at a certain delta T is generating 4,000 BTUs per hour, our target. Now the question is, what is the effect on accuracy of components, including balancing valves, on heat emission on a coil? And before we get into that, we can see that even if we increase our pumping capacity up to 8 gallons per minute, it's all wasted because we're not increasing our heat output one iota, if you will. So we want to stay away from this condition and stay here in our target zone. So back to the issue of accuracy. So let's say that we have a fan coil that has a balancing valve on the same circuit, and we're targeting 3 GPM. So we set the balancing valve to be 3 GPM. Let us say the contractor made some mistakes and didn't quite do 3 GPM. He did 20% off of that. Let's take a look at the effect of that. Well, if he does 20% lower than 3 GPM, which is 2.4 GPM, the output, as you can see here, where you take 2.4 up to where it crosses, is about 3,900 BTUs per hour, or pretty darn close to our target 4,000, 97.5. So not a very large fall off, even though it was off by 20% flow rate. It had a very little effect on the heat output. Same thing on the positive side. If we increase our flow rate above our targeted 3 GPM to 20% of that, to 3.6 GPM, the output then, as you can see here graphically, goes to 4,080 BTUs per hour. So the effect of accuracy is, if you're on the sweet part of the fan coil, is largely minimized, whether you're doing fixed flow rate type systems or variable flow type systems. Now, it's interesting if you look at the ASHRAE handbook, test, adjust, and balance, they kind of emphasize this, referring to the cost of balancing rises with tightened flow tolerance. So yeah, we could put a very expensive balancing valve in there with a small flow tolerance, but you can see you're going to have really diminishing returns in doing so. They also make reference to overflow causes increased pumping costs, as we indicated in our chart, and also insufficient flow reduces the heating and cooling, optimum heating and cooling, because you're on that very quickly changing part of the flow curve as a result of the changes in flow rate on heat output. So let's take a little closer look at a heating application. Here's another air handler, and looking at that, here's our air handler here. It has a coil running through it. Attached to the front side and back side of the coil is our hose coming off of our supply header and going back to our return header. So very common what you see is protecting downstream the components in this loop, a Y strainer. And we'll get into that here in a second. So as we come through and prevent any debris from coming into the rest of the system, by the way, balancing valves don't like debris and dirt. It causes them to be less accurate when you measure flow. So it's always good practice to protect the coil from debris with a Y strainer. As we go through the coil, we come out. Typically there's a control valve. This could be an on-off valve, or it could be a modulating type valve. And on, before we get to a return side of our header here, a balancing valve. Now there's different reasons for putting the balancing valve on the downstream side of our circuit here. One of which is if you're in a cooling application, all right, and you're sending chilled water through your coil here. Chilled water does what? It absorbs heat, and to the extent that you could potentially have some air bubbles in your system, as you absorb heat, water has a tendency to have air bubbles come out of solution, and heat emitters don't like air bubbles for efficiency's sake, as well as in some cases noise. So for that reason alone, as a practice, many designers keep the balancing valve on the downward side of their heat emitter. Now looking at a Y strainer a little bit closer, here's the Caleffi Y strainer. Here's a cutaway view of it, and you can see flow in this case goes from right to left. Water comes into the Y strainer, into the middle of the strainer, gets strained out, going out to the rest of the system. And as that strainer gets full of debris, as you can see over here, it needs to be serviced. So how do you know it needs to be serviced? Well, many times people will periodically measure the pressure drop across the Y strainer cartridge. We have a couple of taps here. I don't know why that tap's missing here. But at a certain value, a pressure drop would indicate that there's a really big plug of debris in here. And so in that case, the installer would pull off this cap, pull the strainer out, clean it out, and put it back in service. So Y strainers do need to be maintained. Now here's an example of another balancing system. We can see right here a balancing valve called a QuickSetter that we'll get into in a few slides. So this is two circuits. Here's a Y strainer and a Y strainer. There's actually another balancing valve hidden behind this insulation here. So what happens is we got high temperature water coming down before it goes through the coil. It gets strained off, goes through the Caleffi control valve or zone valve, down through the heat emitter, and coming back up on the return leg side of it, the balancing valve to the return header. So when we talk about types of balancing valves available to the specifier, one is the globe-type valve. And here we have a cross-section of a globe-type valve. You can see fluid is traveling from left to right. The valve is showing an open state. Now this particular valve type is a flat disc type valve. You can see it's a very, well, flat disc. And from the closed position and turning this valve open to allow flow, as you crack that valve open, the flow rate jumps quickly. The further turning of the valve only increases flow marginally. So it's called a quick opening valve or a low valve authority type of valve. This is not a very good valve to be used for balancing as such because it has such a quick opening characteristic. It's much like on the outside of your house, perhaps you have a water spigot attached to a garden hose. Perhaps you remember, if it's like most garden hoses, as soon as you crack that about a quarter turn, it's almost full flow, and then you can turn it 3 or 4 times after that and have hardly any more flow come out of it. That's a quick opening type of valve by comparison. Now, instead of a flat type of globe type valve, flat disc is a equal percentage plug type, and you can see the plug down here is a little bit differently. It's parabolically shaped, and this leads to as you open it from a closed position, as you turn the valve to open it, it starts off by allowing just a very small amount of water through the valve, and then further turning causes increasing amount of water. So almost in fact, the exact inverse type of relationship as a heat emitter, where a heat emitter emits heat in an inverse fashion, meaning a little bit of flow results in a large amount of heat output. In fact, it's called an equal percentage valve because the characteristic of the valve shown in blue here, as a function of the valve being closed and fully opened, you can see here, as you start to open up the valve, 0 being closed and 100 being open, let's say that 100 equals 10 turns of the valve and this is 0 turns of the valve, 50% would be 5 turns of the valve. Okay? So the combination of the slow opening characteristics combined with the characteristics of a typical heat emitter being inversely related in terms of output results in a linear relationship between how much you open the valve and how much heat is actually being sent through that heat emitter. So it makes for very more accurate estimates of how much flow is going through a valve, or how much heat is being emitted through a heat emitter, I should say more accurately. Okay, but the problem with this type of valve, and here's a shot of it from Dan Houlihan's heatinghelp.com. These are good, but they don't have any means for measuring flow on the valve itself. Instead, you'd have to result in having pressure ports put somewhere else on the system to measure pressure drop to calculate your flow rate. Which brings up a more typical way of balancing is using balancing valves that have the ability to measure flow right on the valve itself. So starting off with manual balancing valves, if we take a peek at what's available in the North American marketplace, you see something like this, a number of valves that probably are familiar to most people watching, very good brands, by the way. On the left-hand side, variable Venturi valves. On the right-hand side, fixed Venturi. So what's the difference? Well, the Venturi is making reference to the pressure ports that are used to determine the flow rate through a valve. And as you adjust a variable Venturi valve, using this one as an example, as I adjust this red knob, the Venturi or the orifice actually changes between the pressure ports, which means that the flow coefficient changes, the hydraulic characteristics changes across those PT ports. That's called variable Venturi. Fixed Venturi, as you adjust the flow rate by changing the valve knob position, the Venturi between the pressure ports does not change. It's fixed. Now this, what does that mean? Well, it means in application, this type of valve has certain advantages over this valve and this valve over this valve, depending on what features are most important to you, and we'll get into that in just a second. So let's look at Caleffi's version of our fixed and variable Venturi balancing valves. Here we have on the left-hand side fixed Venturi. We can see in this orientation, by way of this arrow, flow would be going from right to left. Okay, so the PT ports are on the upstream side of the adjustment mechanism. Now, as I mentioned, the CV doesn't vary across the PT ports as you adjust the knob. Conversely, on the variable Venturi type of balancing valve, as you adjust the flow rate by changing the knob position, the CV value across the PT ports does change. So as an example, you can see we have a level 2 setting here on the knob, and we can go down to our chart for this valve and see that equates to a flow coefficient across the PT ports of 1.6. Now that has an effect on the balancing process that we'll get into here by way of example. It makes it a little bit more difficult to balance this type of valve, which is probably on the down. It's a check mark on the disadvantage side of the valve. So speaking of which, here's a matrix that does a quick view of one valve versus the other type of design in terms of pros and cons. First of all, flow measurement. The procedure for measuring the flow on a fixed Venturi is relatively simple versus variable Venturi, where there's an added step of looking up the CV value since it changes as a function of changing the knob. The number of setting points, adjustment points on the fixed is typically greater and lesser on the variable, and leading to a greater flow accuracy, a more tighter accuracy on this type of valve versus a variable Venturi, as you can see here. Manual balancing valves do not like too many system impurities. The fixed valve is more tolerant of any type of debris in your system, whereas the variable Venturi type of balancing valves is less tolerant, especially as you get into lower flow rates. The flow measurement range is comparable between the two. However, a fixed Venturi valve has a higher maximum flow rate. So as an example, on a certain size pipe, call it 3/4 inch, the fixed Venturi will allow you to measure flow at a higher level than a 3/4 inch variable Venturi balancing valve. That's typically not a real big deal for most applications. The size of the valve, larger on fixed, smaller on variable, and as such, the fixed is typically the higher price than the variable. In Caleffi's cases, this might be 20 to 25%, depending on size, premium for fixed over variable. And all manufacturers will have more or less a similar type of comparison between their fixed and variable type design. So if we look at our fixed in more detail, we do have it from 1/2 inch to 2 inch, 50% glycol, 250 degrees Fahrenheit rated, no lead compliant. So these are third-party certified for the no lead laws in place in the United States starting in 2014, okay, and also starting to take place in Canada in 2014 as well, which means that they're suitable for plumbing applications. Now, if we take apart or cut in half one of these, we're proud to mention some key features, starting with this white washer right here. This is a Teflon stem guide bearing. What does it do? It prevents any type of a high resonant, resonant frequency, high-pitched noise that sometimes balancing valves will incur as water races through the valve, okay? We have an interference between the outside of that Teflon and the cylinder, which it rides in, up and down in, and dampening out any potential noise. That's a really big feature. Another one is the nozzle. It's a stainless, very high-quality stainless nozzle, so there isn't any issues concerning erosion due to particles in your medium. Another important point is the threads used for adjusting the valve. They're dry, meaning they never touch the fluid inside of the system. The O-rings isolate the threads. So here's our double O-rings keeping this side wet and this side dry. Why is that an issue? Well, other manufacturers will have wet threads, and they can seize up in time, especially after long in-operation periods. So if you wanted to isolate the valve after a couple of years and you go to try to change or turn the knob, it could be frozen up on you, a typical issue out there in the marketplace. A very precision calibrated machining process for the Venturi here, and lastly, a highly graduated adjustment mechanism by way of our gear drive up here. So a very high quality valve that we're very proud of, and this is available now in the North American marketplace. Now if you take a look at the valve, the PT ports, and look at what's going on in the PT ports, here's a cross section of the PT ports. They have an EPDM packing in them. Through the middle of the packing is a opening which is typically closed and sealed when in operation, but when it comes time to use to measure the pressure, a needle gets pushed down, opening up the opening, if you will, exposing the bottom of the needle to the hydronic system where you can measure pressure from. Now, a word of caution: as you pull these needles back out, do it slowly to allow time for the EPDM to shrink around the needle as you're pulling it out. If you pull it out too fast, there will be a momentary exposure of the hydronic system to ambient, causing a squirting and problems associated with that. So just a little point for you. Now, taking another look at the valve, we can see in this example that the valve has been set to 4.5. We'll talk about setting the valve here in a few minutes. And then a wire lock tab to prevent it to be tampered with. And then lastly, if the valve in the future ever needed to be used to isolate the rest of the system, you can turn the valve down to isolate it, and then without having to recalibrate the valve, back it off and remember where the setting was so that you're back to the original position, the original flow rate. Okay, let's talk about measuring flow rates in a balancing valve. Here's a, albeit blurry shot of a contractor. This is a balancing valve over here. We can see it's a variable Venturi type of balancing valve, just a word of note. And it doesn't require real sophisticated tools to set flow rates using a balancing valve. Here we have an analog differential pressure gauge this contractor is using, and knowing the differential pressure and the flow characteristics of that valve, that contractor can set the flow rate, which we'll show by example. Now, there's a number of digital instruments in the marketplace, as you can see here, for measuring flow rates through a balancing valve. Interesting, here's a close-up from Pete'sPlug.com of their, you can see the end of the needle with an exposed hole, much like the pump-up needle you use for inflating your football or your basketball, much the same kind of technique, if you will. And then when the needle isn't being used, a protective sleeve can be screwed down to prevent that needle from being compromised during transit or storage. Okay, when we look at adjusting the flow rate on a balancing valve, I'd like to start off with an electrical analogy. We remember from high school class DC circuit, and using Ohm's law, we know that if we have a battery as an example and a resistor, we can calculate the amperage by this Ohm's law. So, for example, if we had a 12-volt battery and a 3-ohm resistor, we know that we have basically 4 amps of current, assuming there's no resistance in our wiring. So very straightforward, and by analogy, hydronics also has a very similar formula for any type of device in a hydronic system, whether it's a zone valve, a balancing valve, or a straight length of pipe. The formula is flow rate equals the flow coefficient of the device times the square root of the pressure drop. Okay, so it's similar but a little bit different than the electrical analogy. So as an example, if we have a device that we measure the differential pressure across that device as being 9 psi, and flow coefficient we know in advance is 7, we can plug it into our equation here and see that the flow rate is 21 GPM. Okay, so going to our balancing example now, we're going to balance a circuit using a fixed Venturi balancing valve. In Caleffi's literature will be the size of the valve, starting at 1/2 inch up to 2 inch, and the Venturi flow coefficient. So the flow coefficient of the Venturi. So we can take the formula that we saw in the prior slide, F equals CV times the square root of the delta P, and apply it to the Venturi. So for example, if we put a pressure differential gauge across our ports here, and we measured 3 psi, and we're using a 3/4 inch balancing valve, which means in advance we know that the CV is 6.4. Well, we can use our equation, 6.4, which is the CV, times the square root of the pressure drop, equals 11 GPM. Voila, very easy to make that calculation. Or we could take the instructions from the product itself, the instruction sheet, which has a chart dictating flow rate as a function of pressure drop. And you can see there's 6 bars indicating the 6 different sizes of balancing valve, 1/2 inch up to 2 inch. And since we are working with a 3/4 inch valve, this is the line that we'll be working with right there. So we take 3 psi that we measured, we go up to 3 psi, right here, take it across where it crosses our 3/4 inch line, and take that line down, and very conveniently we can see that that equates to, voila, 11 GPM. So whether we do it by lookup or by calculation, we arrive at 11 GPM. Now, the prior equations hold true when we're talking about water. If we're talking about a medium in our hydronic system other than water, we have to add a factor if the medium has a density significantly greater than water, and basically adjust it by the ratio of the two densities, water and the fluid that we're measuring. So as an example, let's say we have a antifreeze solution of 20% ethanol and 80% water, perhaps a geothermal system, okay? And our measured flow rate, as we showed in that prior example, was 11 GPM, but we're not using water, we're using this antifreeze. We simply take our 11 GPM that we calculated down here, okay, and then we multiply it by the ratio of the two densities, giving us 11.5 GPM, okay? So that's how you would handle fluid other than water using the charts. Now, a question comes often, what orientation can I put these balancing valves? Well, you really don't have any limitations. You can have them upside down, vertical pipe, horizontal pipe, it doesn't make any difference. As I mentioned, there is some sensitivities to the flow rate measurement as a function of turbulence, so you want to minimize turbulence. So keep your pipe diameters from your elbows greater than 5, greater than or equal to 5. And if that elbow is preceded by a pump, double that up to 10 pipe diameters, just to be on the safe side. Coming off the discharge side of any pump is always a vortex action, and so a couple more pipe diameters to allow that to smooth out helps with the accuracy of the balancing valve. Okay, so we looked at the balancing process for a fixed Venturi balancing valve. Let's look at a variable Venturi balancing valve, and here's a shot of Caleffi's variable Venturi balancing valve. Now, we'll use ours as an example, but it's a similar procedure as any other balancing valve out there in the marketplace. These balancing valves, by the way, are not available yet in North America. They will be sometime mid-year. These caps right here are where the pressure ports would otherwise be installed. In fact, when we come out with the balancing valve, we'll have the PT ports pre-installed for the market. So let's take a look at the slight difference in procedure for balancing using this type of balancing valve. So we'll use our same formula. That doesn't change. The rules of hydraulics doesn't change, hydronics. And so we're going to also use a 3/4 inch balancing valve like we did in the fixed Venturi example. Okay. So one variable is that we have to know, by way of where our knob position is, what the CV, that tells us the CV value, okay? So on the 3/4 inch valve, if you look in our literature, we can see that at knob level 2, the CV is 1.72. So we got that part of the equation. And if we measure the differential pressure across our ports here, and that was 3 PSI, we substitute those values into the equation, and we get 3 GPM, okay? Or, like we showed in the previous example, we can do it by way of lookup. Now, the charts on a variable Venturi type balancing valve, each size valve, 1/2 inch, 3/4 inch, each size has its own chart, whereas fixed Venturi has all sizes on one chart. Why is that? Well, it's because the CV value changes as a function of the knob position. So this is a chart for the 3/4 inch valve as an example. So what we're going to be doing is working off the graph that is associated with position 2. So there's position 1, 1.5, 2. So there, okay. So we're going to take our measured 3 GPSI, come across to where it crosses 2, take that down, and we can see again 3 GPM. So by way of lookup or by way of calculation, we have calculated 3 GPM going through the valve. Just a quick shot of one of our prototypes in the development of the valve the last few years. Okay, so let's talk about sizing and presetting. Now, typically in sizing and selecting a manual balancing valve, if the rest of your circuit, so as an example, if the rest of your circuit is 3/4 inch, your fan coil is 3/4 inch, your zone valve is 3/4 inch, and you have used the proper flow rates to determine those to be used, typically a 3/4 inch balancing valve is going to be sufficient, but perhaps not. And so we're going to talk about that. So we'll talk about sizing. And then the issue of presetting. Presetting is a way of predetermining the knob position for a balancing valve to give you the desired flow rate on that circuit, thereby making the balancing contractor's task a heck of a lot easier. So we'll talk about that too. So back to selecting a size. So the biggest criteria is to minimize chances of low flow turbulence inaccuracies, or basically the effect of turbulence when you have low flow rate. So what you want is to have your balancing valve operate in application of pressure drops greater than 0.4 psi. That gives us proper valve authority, if you will. All right. So we want some pressure drop to the extent of 0.4 psi. Okay. And if we take our formula and rearrange it, it's another way of saying that our flow coefficient on our balancing valve, the maximum flow coefficient is our flow rate times 1.6. Okay, I just rearranged these values using our 0.4 up here for the delta P. Okay, so we can just take, as an example, if our flow rate, design flow rate is 4 gallons per minute, okay, that's F, we simply multiply that by 1.6, and that tells us our flow coefficient that we don't want to go above our maximum flow coefficient for a balancing valve. And maximum means with the valve fully open, okay? So if you look as an example at Caleffi's 6 different sizes of balancing valve, all right, 2-inch, 1.5, 1.25 inch, down to 1.5 inch. And for each size, we show the flow coefficient as a function of the knob position with the knob fully open, okay? With the knob fully open, here's the CV value. So we can see that 2-inch has a maximum flow coefficient of 31. Well, we don't want to be above 6.4, so that's way too big. 1.5 is 2-inch is too big. In fact, anything 1 inch or greater has too much of a open valve flow coefficient. Okay, it's not until we get into 3/4 inch and 1/2 inch that we have flow coefficients under 6.4. Okay, so the 1/2 inch and the 3/4 inch would be okay to use in our case where we want to control flow to 4 gallons per minute. So let's take a look at presetting. Okay, so presetting is establishing the value to set the knob position for each of our manual balancing valves. And we're going to just do one, just for example. And we're using an illustrative situation where we have a boiler and a pump in 3 zones, each zone controlled by its own zone valve. And each of these zones has the zone valve, the heat emitter, and the balancing valve. All right. So our task is, again, we want to preset these so that it makes the task of balancing. And by the way, balancing is an iterative procedure. You would start off by setting the flow rate on one, adjusting the flow rate on another, which changes the flow rate on this one because your pressures have changed, and it requires 2 or 3 iterations at a minimum for contractors to adjust manual balancing valves to get to the desired flow rate in each of their circuits. It's a topic for another webinar. It takes some time, but to make that task extremely easy, if the designer has predetermined the setting, it will take a lot of the labor out of that process, and that's what we're going to do here by way of example. So let's say each of our crossovers is a 1/2 inch copper pipe, okay? And let's say, for argument's sake, that our design flow rates is 6 GPM, 5, and 4, each of those zones. And let's say that we have established our system pressure down at the boiler to be 12 psi, where our expansion tank perhaps is set. And let's say that the designer lastly has decided that in order to accomplish these flow rates with these size crossovers, he estimates that his ECM pump is going to be set at 7 psi constant differential pressure. So it's a variable speed pump. But we could have used 8, we could have used 5, and maybe none of those could have been sufficient, in which case we'll have to do the calculations all over again, but this will work out, trust me, just for example. Okay, so we're going to set the value of the knob for this balancing valve. So what we need to do that is to determine the differential pressure across this crossover, because if we know the pressure drop across this crossover, all right, then we can separately calculate with this flow rate the pressure drop caused by the balancing valve and the pressure drop caused by the heat emitter, which leaves us this pressure drop that can be easily figured with a simple equation. So that's what we're going to do. So let's say that our design conditions are 15 GPM, all right? So a starting point is the point of no pressure change, is where the expansion tank adjoins the hydronic system. So under design conditions, we're sending 15 GPM. And just for argument's sake, let's say that we calculated that through this leg of piping and through our boiler and through this leg of piping, we have had only 1 psi pressure drop. So if this is 12, that means going into the pump it's going to be 11. And because the pump is operating on 7 psi constant differential, we know that it's going to raise the psi up to 18 coming off the pump. So right at the first crossover, one of our variables is now solved, 18 psi coming off the pump and on the first crossover. Okay. Similarly, starting back at 12 psi again, and we know there's 15 gallons per minute coming down through here, right? We can calculate the pressure drop through this leg of our system. Now let's say for argument's sake that's 1 psi. So if this is 12 psi, that would make this 13 psi. Okay? 13 psi minus 1 equals 12. So now we have the pressure differential across over here. So now we're getting closer to determining what our presetting needs to be. So let's take a closer look at that, clean that last page up here, and here's what we have. So we have 18 over here that we calculated and 13 over here. So one of the things we know is that the pressure drop across a mains is equal to the sum of each of the individual component pressure drops. So the pressure drop of the zone valve plus the pressure drop of the heat emitter plus the pressure drop of the balancing valve, you can sum those up and it's equal to the pressure drop across the mains. We can rewrite this for the pressure drop across the balancing valve simply by algebraically rewriting it, and now we have the formula for calculating the pressure drop across the balancing valve, and once we have that, we can set the knob setting. So starting off with the zone valve, if we have a half-inch zone valve, and Caleffi's literature indicates a flow coefficient of 3.5, we can take our formula between flow rate, flow coefficient, and pressure drop and rearrange it and calculate the pressure drop being the flow rate squared divided by the flow coefficient squared equals 1.3 psi. So now we've calculated the pressure drop across the zone valve. Let's go on to the heat emitter. Let's say we have 8.5 feet of heat emitter. Now manufacturers of baseboard and other emitters will publish pressure drops as a function of flow rate. That's one way of determining it, or there's many hydronic formulas out there in the marketplace that can calculate this. You can use either one and find out that the pressure drop in this case is 0.68 across the heat emitter. Okay. So now, because we know that the mains pressure drop is 18 minus 13 is 5, we can substitute all that to calculate the pressure drop across the balancing valve. 5 minus 1.3 minus 0.68 equals 3.0 psi. So we know now that we want a pressure drop across the balancing valve of 3, and we know that there's going to be a flow rate of 4 going through here. And with these, we can determine the preset value to set the knob to. So we go back to our chart for the pressure drop across the entire valve now. Now this is a different chart. It's across the entire valve. All right. It's not across the ports because the pressure, the CV doesn't change across the ports. So we can go to our instructions and we can see for our 3/4 inch valve, the knob position, the delta P, and the flow rate. So we can take our 3 psi pressure drop and a 4 GPM flow rate, our target pressure drop, and a 4 GPM flow rate, and where they intersect we see is here. And we know that that's not quite to the position 2.5, and it's a little bit less than position 2. And if we eyeball that, we'd say that's probably about 2.3. So we would take our balancing valve and adjust it to 2.3. And now we have preset the balancing valve, making the balancing task very simple. Now, as you can see, balancing takes time and training, and the question is, what happens in practice as a result of it being difficult? Well, sometimes you get cases where the balancing valve on a coil isn't even adjusted, like in this case where this balancing valve is left fully open, in which case that might cause too much velocity going through this coil, leading to pinhole leaks, erosion of other effects, noise, and improper heat transfer, actually. So how do you simplify the task of balancing? Well, you take the labor out. And one of the things that we did a few years ago is introduce into North America a balancing valve that does just that without any use of pressure transducers or devices, you can directly read on the valve itself the flow rate going through the valve by way of this bypass loop. So basically what the contractor does, pulls the pin, and while looking at the flow rate going through the valve by way of where this bead goes on the gauge, he can adjust the valve to its desired flow rate. And if you look at a cross-section of this, here's what you get. Here is that little bypass loop here. Normally no flow is going through here, but as when the contractor pulls this pin, it induces a flow by way of a Venturi right here through this bypass loop. And this is a magnetic disc right here attached to a spring. And that disc here in red is attracted to that ferrous bead. Okay? And it's calibrated in such a way that when you look at it straight on, that bead rides up to indicate in gallons per minute the flow rate. So if you pulled the pin and you had 6 gallons per minute and you wanted 4, you simply take this knob, adjust it to the bead dropping down to 4, and now you have set your flow rate within literally seconds without any instrumentation needed. So if we look at this example, this would indicate, if you can see it on your screen, about 3.4 GPM. And here's the task of, here's how easy it is to adjust. Here's a contractor on a chilled water loop adjusting the balancing valve. And we have used these, seen these used in many applications around the country. In the interest of time, I'll just go through them very quickly. Even solar thermal collectors, where you have a series of arrays. Some contractors will balance each separate array individually with a balancing valve, or use reverse return piping and use a master balancing valve, if you will, to set the flow rate so that all of these each of these 3 arrays has the same flow going through it. Like this example in Milwaukee on the solar thermal installation called Growing Power. Now, before I leave solar loop balancing, we do have a balancing valve used in our solar pumping stations. It also has a visual sight gauge and a slot where you can take your screwdriver and adjust the flow rate to dial in your prescribed flow on that solar loop that the pump is driving flow to. Back to balancing valves of QuickSetter type. Geothermal guys like to use these valves. I mentioned early on in the webinar, they may have mentioned anyway, the importance of ground loops having turbulent flow so you get adequate heat transfer in your ground. And so to make sure that's happening in each of your loops, contractors bringing in their ground loops and terminating them on an inside manifold, and each loop having its own balancing valve makes a very precise way of ensuring proper heat transfer to and from the ground. And we see these in many cases of jobs that were submitted into us, geothermal loop with quick setting balancing valves. More examples. Okay, we're going to jump to plumbing now. Balancing hot water recirculation circuits. Now, traveling the country, we hear from engineers, it's always a task to try to, in a hot water recirculation system, get the risers to balance out to ensure proper flow to each of those risers. And the issue of hot water recirculation has become a more and more commonplace in North America. Here's the Wisconsin Building Plumbing Code that indicates either using electrical tape or hot water recirculation are the means required. Here's a map of the United States that basically, in a nutshell, indicates because of demographic changes in the west and southwest part of the United States and increased water consumption, a increase in the amount of codes requiring hot water recirculation and plumbing systems. So if you look at a plumbing system, here's a hot water heater, and a typical hot water heater supplying hot water to a number of fixtures. Because of these fixtures are in close proximity to the hot water heater, when there's a draw on one of the faucets, there's no waiting for hot water, no issue, very little waste of water. But when you start getting into more commercial systems and there's a long run between your source of hot water and where it's being consumed, the heat loss in these pipes could result in a significant wait for hot water when someone turns on a shower or bath or a faucet. Not to mention the annoyance. There's the annoyance factor and also the wasted water factor, and water is getting more and more costly, as we all know. So in these applications, many designers will specify a hot water recirculation system whereby a pump is installed and a parallel riser is installed to constantly take hot water up close to the last fixture back to the heating system, so that whenever there's a draw, there's always hot water available with very little waste. Okay. Now, the flow rate in each of these risers depends on how much heat loss is in the insulation. It depends on the water quality. Many engineers like to specify a half gallon per minute for each of the risers, sometimes one. Perhaps the biggest factor is water quality, but we see half gallon per minute probably is the most common. So if you wanted a half gallon per minute going to each of your risers, you might put a pump that's capable of generating 1.5 gallons per minute, in which case you might get a very unbalanced system such as this. The risers closest to your pump are stealing most of your water, and the ones furthest from the pump are getting starved of water, even to the point of no flow. Okay, so we have an unbalanced system. So just like hydronic heating systems, there's a need for properly balancing plumbing systems. So a good way of solving that is to install balancing valves on each of your risers, such as we've indicated here, and a temperature gauge, and maybe even a check valve to prevent thermal siphoning, okay, like this. Okay. Now we have the ability to dial in a half gallon per minute on each of these. So by putting in a half gallon per minute on this, we create more head available for flow to go to each of our risers so that we get our prescribed half gallon per minute required in each of the risers. Okay. Now, a close-up of this little design detail we have created in a compact package called a QuickSetter Plus that's now available in the marketplace. It's a lead-free balancing valve. It's available to the designer in two ranges of flow, from half gallon per minute to 1 3/4, and also 2 to 7, and conveniently union sweat connections on the supply and discharge side of the valve. Also a built-in check valve and a temperature gauge, optional temperature gauge, and a stainless ball adjustment mechanism here for high durability. So a close-up look at the valve face. Here's the half gallon per minute, 1 3/4 gallon per minute, and 2 to 7, and the optional temperature gauge close-up. Okay, we're going to close on pressure-independent balancing valves. Now, pressure-independent balancing valves means balancing valves that are capable of maintaining a constant flow rate regardless of pressure changes on the circuit that the valve is installed in. So as circulators turn on and off, and as control valves turn on and off somewhere else in the system, it doesn't affect the flow rate on the part of the system that the balancing valve is controlling. So flow is independent of pressure changes. That's a pressure-independent balancing valve. Okay? So by way of how these are applied, let's start off by stepping backwards to a manual balancing valve again. So this is a similar circuit that we saw earlier. We see 4 zones, a pump, a fixed-speed pump, a boiler. Okay. Now, under design conditions, perhaps we set our balancing valve to on the top zone to be 6 gallons per minute, 4, 8, and 4, delivering 22 gallons per minute. Now, what were to happen if the zone valve here were to turn off? Say the thermostat says I'm warm enough in my room and turn off by looking at this. Well, what is going to happen is this. Zone valve turns off. Now that pump wants to deliver the same amount of head to lesser circuits available to it, so it's going to end up increasing the flow rate to all of the zones remaining open. So 4 turns into 4-6, and 4-6 turns into 6-2 as an example. Okay, that might not be a problem, but now how about if this zone valve closes off? Now you only have 2 zones open. Now you might be getting 10 up here and 6 up here. And then in the worst case condition, you have only 1 zone calling, and now you're vastly over pumping. That creates problems. Now, before we leave this manual balancing valve example, one solution that the designer could do is install a differential pressure bypass valve from the supply side back to the return side of the pump. This would absorb any excess flow that otherwise gets sent through the zones if you don't use a differential pressure bypass valve, meaning all of the valves stay at their design flow. Okay, so it adds a little bit of cost in doing this, but it keeps you at good control. Alternatively, the designer could specify, instead of manual balancing valves, pressure-independent balancing valves as such. Okay? So when this valve, again, as we showed in our other example, turns off, what happens? Well, it turns off and all of the flow rates stay constant. Okay? And there's no need for a differential pressure bypass valve. So this is where pressure-independent balancing valves are used in these type of applications. Okay? Now, if this valve were to turn off, these would continue delivering 4 and 6 gallons per minute respectively. Okay? How do these work? Well, if you look at them and you take them apart, they have a cartridge inside that contains a piston and spring mechanism. Okay? So if flow is going through the cartridge left to right, as you see by the arrows here, okay, flow goes past the cartridge and through this opening right here. And as pressure builds up on, if the pressure increases on the circuit, the piston compresses, as simulated by my finger here, pressing that piston down. And as that piston depresses, the opening available for flow to travel through decreases. So we have increased pressure with a decreased opening. The result of the combination of the two results in a constant flow regardless of the pressure changes. So as that piston goes up and down with pressure changes, the flow rate stays constant. So that's a pressure-independent balancing valve cartridge. Now before we leave that, the 10.0 on here would indicate 10 gallons per minute. This is a 10 gallon per minute cartridge. And here's a graphic indicating that constant flow range that the valve works within. So you can see here anywhere between 2 psi differential and 32 psi, the flow rate will always remain constant. So that becomes the working range. It's quite a large range for most hydronic applications. And here's a depiction of the balancing valve unassembled or disassembled. It's also a low noise cartridge. It's a polymer cartridge, so it leads to anti-scale and also sound deadening, so there's no vibration effects. And it's also lead-free. And here's an example of that particular valve used in heating applications. You can see, as it leaves our factory here in Milwaukee, we put the flow rate on the valve itself. So 3/4 gallon per minute, half gallon per minute, half gallon per minute. Here's another example of the pressure-independent balancing valve. You can see right here in a geothermal pump and dump application. And looking at the other configuration of pressure-independent balancing valve, it's got pressure taps, whereas the other one didn't. Now the pressure taps aren't used the same way as a manual balancing valve. They're used to measure the flow rate to ensure that the pressure drop is in that operating range I showed you, that 2 to 32 psi. As long as that's the case, then the designer knows that the flow rate going through here is at that established value, that fixed value. And some shots of a pressure-independent balancing valve with a Y strainer protecting it. Another pressure-independent balancing valve on a hydronic radiant heating slab application. So we have flow coming down here. Before it gets to the manifold, we are controlling the flow rate and then coming back through the control valve to the return header. Another application. And lastly, another application of a pressure-independent balancing valve. So today, this is the end of our webinar. We talked about manual and pressure-independent balancing valves, the difference in design construction. We talked about applying balancing valve in both heating and plumbing applications. We hope this was beneficial for you. When you get a chance and you have an interest, take a look at our other training videos online. Thank you.